All right, just for those who are new, a little bit of history. Geophysics department is now 100 years old. It was in this issue of the American Association of Petroleum Geologists in 1926, where it was announced that a geophysics program would be constructed as the world's first at the Colorado School of Mines. Quite monumental for any educational program to last for 100 years. And on this centennial year, it's great to have another field session. Field session has always been an integral part of Colorado School of Mines field camp. On the left is a flow chart explaining the sequence of courses that students had to take in the 1950s to get a degree in geophysical engineering from the Colorado School of Mines. And notice even then, it was really important to have applied field applications. This is a version of our current flow chart where the students still funnel into sort of this signature experience where they take their laboratory and classroom activities and take it to a new environment and do it in the field. Through time, we've seen lots of changes in the type of equipment that we use. On the left, some of the fun equipment we've used in the past. Moving to the right, we move into a digital arena. A lot of the technology has changed, but our goals have remained the same. It's teaching our students to take the technology, the theory, the physics, the applied applications that they have, and understand the Earth system through remote geophysical techniques. A quick plug on that 100-year anniversary. We'll be having a celebration September 18th and 19th. You can email me if you'd like more information. We are just about, Rachel, to send out an announcement through the foundation about registering and getting information for people to come, share memories from the past, meet current people in the program, and think about the next 100 years. So what have we been doing for the last month? Fast forwarding quite a bit. Our students start out with a geology tour from Golden all the way to Steamboat Springs, where we've been conducting field camp for the last handful of years. Right. Geology is the foundation for geophysics. If we didn't have the rocks and fluids on the subsurface, we might not need to explore them. So they start out with a geological tour, and then we start moving into their geophysical applications and techniques. And you'll notice that there's some maybe historical aspects here of carrying batteries and equipment up fields to do surveys. Some of us study a marine environment. We now actually do some lake geophysics surveying at Stagecoach Reservoir. And the students are doing the work, but they're supported by a series of instructors. Here's Dr. Manika Prasad, helping control traffic so our students could do a seismic survey in a pretty busy part of town of Steamboat Springs. It's a cooperative effort. The activities are led by the students and the instructors are all supporting them. It's quite a fun activity. Just all kinds of different things. Everything from, again, more traditional sort of field geophysics, looking at hill slopes, more engineering applications of maybe looking at what a dam might look like and how we could use radar to understand these problems. How we can shake the ground. Our students get to get in and use a vibra-sized truck to help image the deep reflection seismic. They get to tow sleds around. And something that we harp on the most, and this kind of ties back to the geology, is where are we doing this in the world? We have to have good location information so we can put our geophysical data in geophysical context. Why Steamboat Springs? This has been an exciting destination for us since 2022. This is not, I learned this year from some of our students who really dug back into the literature from the old 1800s. There are a handful, maybe two handfuls of papers that have been written on the geology of the Steamboat Springs area. This was a ripe opportunity to bring our students out and learn more about the geology of this hydrothermal system, near surface landslide problems, hill slope problems, water problems that affect the entire environment. And in the 5 years that we've been there, our students have produced a handful of 4- and 5-page papers expanding what we know about Steamboat. Each class of students pushing farther beyond what the previous group did. So we're learning from the previous years and expanding on what we've done, and we're doing it better. And now I'm going to hand it over to our students to introduce the overall projects that they helped design and then present some of their results.
Thank you, Brandon, for the introduction. Hi, everyone. Thank you for being here. Thank you for spending your afternoon with us. We just want to give you a brief overview of what we've been doing for the past month and what we did in our 2 weeks in Steamboat specifically. So we're all rising senior level students in the geophysics field camp. I'm Lillian Hansen.
I'm Auckland Sacco.
And I'm Alex Lerner.
So what is geophysics? We're studying the Earth using processes. We're doing subsurface imaging. It's a really non-invasive way for us to understand what's going on below us. And understanding the subsurface, we can see things like geology, we can see mineral deposits, we can see soil moisture levels, and then also faults and hydrology.
So what do? We went to Steamboat Springs for 2 weeks and we collected all sorts of data. We did this with multiple different methods, including ground penetrating radar, some electromagnetism, some seismic surveys, and we really studied the subsurface structures as well as the geology in the area in the greater Steamboat area. We also got to learn a lot about Steamboat from the local community, as their interactions with us are very, very crucial to this whole process.
We also want to extend a huge thank you to everyone listed here. Without them, none of this would have been possible. So we really want to thank them for their support. So as Brandon mentioned, the first thing we did was start off with a geology background of the area. So we learned about kind of how the different layers of rocks got laid down. We talked a lot about how some of the hot springs differ from the other ones. So like, while some of the hot springs had odors and were at a lower temperature, and then while some of the hot springs like the Old Town Hot Springs and Strawberry Hot Springs were warmer and were more swimmable. We also talked about the Yampa River and then the Basin for that.
So the first survey site we spent a ton of time at was the Lithia Springs area. There's a site here called Lithia Springs, and there's another spring close to it called Critter Spring. We used a couple methods here. We used ground penetrating radar, near surface seismic. We did a gravity survey, and we also did an electric receptivity survey here.
So one of our next survey sites was Stagecoast Reservoir State Park. We were very lucky to get free access to the reservoir. Didn't have to pay for parking, which is very great, especially when we're there for 2 weeks. But there we used a remotely operated vehicle. It's like an underwater drone. We also used a CTD device, which is conductivity, temperature, and depth, which dips down into the water and gives all these readings, as well as we did some more ground penetrating radar in the area.
Another one of our survey site was we had a seismic line running along Route County Road 14 and Route County Road 22. Along this, we did reflection seismic where we had a vibro-sized truck send energy into the ground, which bounced off the different layers and got read by our GTI nodes. This is a minimally invasive method. It's kind of like an ultrasound for the Earth. And then in more of the communal areas, out of respect for the community, we use a propelled energy generator to kind of create those waves.
We also did GPR all over, so we did that in a lot of our different survey sites. We did it on Howelson Hill, we did it by Black Sulphur Spring, we did it over the Sulphur Spring Cave, which is really cool, and we also imaged some of the areas around Stagecoach Reservoir.
So what are you going to see today? For our presentations, we first off have a seismic and geologic insight presentation. Then we'll get characterizing travertine. We have a multi-physical analysis of Lithia-Critter. From there, we have a case study of the Sulphur Spring Cave. There's a geophysical hunt for the historical Onyx mine. And then lastly, we end with some imaging of some local geology around some train tracks. Thank you for coming out.
We'll move into the first group's presentation. We'll have a little bit of time for questions at the end of every presentation, and then we'll have time for general questions and discussion at the end as well.
All right. So our group spent the last couple of weeks working on a seismic and geologic insight into the Yampa River Basin, talking about processing, modeling, and interpretation of that basin.
I'm Lillian Hansen.
I'm Benjamin Kohler.
I'm Alex Lerner.
I'm Auckland Sacco.
I'm Zach Schallenberger.
Okay. So some of the things we're going to be talking about today is giving a little bit of motivation and context behind our project. We're going to talk about the data methods and acquisition. We're going to talk about seismic processing, seismic interpretation, and then the geologic interpretation from that processing.
So let's get into some motivations and context. Where are we doing this project? Why are we doing this project? Starting off, we're in Colorado. Specifically, we're going to be in this northwestern corner of Colorado. This area is largely covered by the Yampa River Basin, and that encompasses about 1,471 square kilometers of that area. This basin has a really big impact on the entire area around the Steamboat Springs. So the Yampa River is mainly fed by snowmelt from the Rocky Mountains. There have been about 6 really big glaciation events in the area, starting 300,000 years ago up to about 12,000 years ago. The glaciation has created valley systems and deposited outwash in the area. This continues to influence modern drainage patterns, and it added a lot of sediment distribution. So there's a thick sequence of alluvial deposits sitting on the top of the basin, and then there's also some older sedimentary units and a really prominent crystalline basin underneath the basin that exerts a structural control on all of the overlying sediments.
Well, this is our main geologic area that we're looking. There's that upper quadrangle right there. And again, once again, the geology is very, very important to what we're doing. This is that map. This is our geological surface map. And we can kind of zoom into the surface or the area that we're looking at. Up there, we have Steamboat Springs. And then where we did our seismic line is in this little area. We can see 3 distinct layers. First off, we have our Browns Park layer. This is going to be some sandstone, siltstone. We have an alluvial. And then we also have this older gravel glacial. This geologic context is very, very important to what we're doing for our seismic interpretations. And from that, we can make some initial geologic hypotheses. We have a north-south cross-section here, as well as a west-to-east cross-section or east-to-west cross-section. This is our initial interpretations of what we think the different geology might be like under the subsurface of where we're doing our survey.
Awesome. So let's get into some methods how we acquired our data in the first place. So for this, we use reflection seismic surveys. These surveys allow us to image the geology beneath the surface by sending acoustic energy waves into the ground. Like Auckland said, you can kind of think of it like an ultrasound, but for the Earth. We had a Dawson Geophysics vibro-sized truck, and that generated these waves by putting a large metal plate against the road surface, and it sends pulses of energy down into the subsurface. The waves that are sent down are called instant waves, and they travel down through the Earth, and they encounter different boundaries between rock layers. When the waves hit a boundary between the rock layers, some of the energy can bounce back up to the surface as a reflected wave. The denser or more different those rock layers are from each other can give us a more strong reflection. Our GTI nodes, which were placed in the ground along our survey line, recorded the arrival of these reflected waves. The key measurement here is going to be the two-way travel time, so that's how long it takes for the wave to travel from the truck down to that rock boundary and then back up to our nodes that are recording. Deeper layers take longer to return than the shallower ones, so by measuring these travel times across thousands of node shot combinations along our survey lines, we were able to build a picture of where each rock layer sits beneath the subsurface.
So our GTI single component and our U nodes were deployed over 2 different survey lines. The first one was along Route County Road 14, which is in this red here. And then that one had a total of 787 nodes. And then also along Route County Road 22, which is this blue line right here, which had a total of 231 nodes. This is the vibro-sized truck that shot all of our waves into the ground. For our survey, the shots were stacked 8 times at each source location, which is essentially sending the same wave multiple times and averaging the recordings to reduce noise and produce a cleaner image. And then when we were back in Golden, this data that we collected was integrating with existing seismic profilings collected during the 2022 Geophysics Field Camp along Colorado State Highway 131, which used a denser node spacing of 5 and 10 meters.
So now that we have all this data collected, we need to process it all together into a coherent and readable format. And we accomplish this using a workflow that's simplified here, starting out with pre-processing and working all the way through depth conversions and migrations, which will help us to produce some interpretable images. Since our nodes are recording 24/7, we need to isolate the time period where we're actively shooting energy into the ground and hoping to receive it back at our nodes. That data looks like this, where we can see the data is recorded along the line as the shot has gone off. We then group this data around, we organize it around a central point, which we call a common midpoint gather. And these gathers are then stacked together into our brute stack, which is our first real look at the data. And there are several things to point out here. Firstly, we see this very weak response throughout the entire circled area, where we would expect to see some reflections based on our superficial geology that we mentioned earlier. Next up, we also see some reflections down below this stronger reflector, These are secondary reflectors reflections off the basement where it has come back up to the surface, reflected back down, and come back before it was ultimately picked up by our nodes. With a deeper time section, we would see more of these at multiple intervals of that time. Moving into signal enhancement, we need to consider the environment that we've collected this data in. Along our survey lines, there are cars, people, and the movement of the earth that are causing noise in our data. And our goal is to make our signals stick out above all of that noise. We accomplish this by filtering out certain frequencies and applying gain control to make our responses stronger and more visible. In our case, we applied bandpass filters with low cuts ranging from 5 to 20 hertz and high passes ranging from 40 to 70 hertz. We chose these frequencies based on what we expected to see returned from the subsurface, as well as previous field camps' experience with processing. Additionally, we applied some muting from stretched signals that were apparent in our data from other processing steps. This helped us to see the actual signals more clearly. Most notably, after filtering, muting, and gain control, we see several more distinct frequency packages appear closer to the surface, where we'd expect to see some reflections. However, there are still some points in the section that aren't fully processed yet, and Zach will cover the next steps now.
So a big factor that controls when our signals arrive at our receivers is the velocity structure of the subsurface. And to know where our signals are bouncing off of, we need to make a velocity model of the subsurface. This accounts for how velocity changes with depth, how it changes along our line, and also localized near-surface variations. As we refine our processing parameters, we can see a clear evolution of our velocity models here. This is an early model from County Road 22, and we can see that it generally gets faster with depth, which is expected, but it has very significant velocity changes along the line, which is unlikely for such a short seismic section. This was our second iteration. We can see that it is smoother for the shallower layers, but the deeper layers still exhibit a lot of changes along the line. And this was our final velocity model. It shows smooth and consistent variation along the line, and we can see some variation, especially in the deeper layers, but these are small enough that we consider them geologically plausible. So up through this point, all of the data that we've been working with has a vertical axis of two-way travel time, but we want to know the actual depth of what we're seeing here. And the way we do that is by applying that velocity model we made in the previous step to the times that we record our signals and getting them as a depth. After this, we apply a migration algorithm. Migration is what transforms our reflected signals into a high-resolution image of the subsurface. This is what County Road 14 looks like before migration. This is what it looks like after. So as we can see, just this one step has a huge impact on the outcome of our seismic section. We can see that this makes our reflectors a lot easier to track all the way along the seismic line. So the main line that we worked on for County Road 14 was County Road 14 in 2026. So it begins just south of Steamboat and it extends around 8.5 kilometers to just past the intersection with County Road 22. And we actually placed receivers further north up through the city of Steamboat, but vibro-sized trucks can cause small vibrations in the surrounding area. So we opted to stop shooting just short of the city limit to be respectful to the community. We can see here that our deepest reflector ranges from around 550 to 400 meters. We have good reflections in the southern end of the section. However, in the northern end around here, our reflections are a lot less coherent. However, throughout the whole line, we can still see a clear deepest reflector and several shallower reflectors that we can use to make some interpretations about the region's geology and structure.
Moving on to our secondary line, we have the finished section for County Road 22. This line runs west to east, covers about 3 kilometers, connecting to County Road 14 on the west side and intersecting Highway 131 approximately in the middle of this section. The most prominent feature on this section is located here between a depth of 450 and 650 meters. We can see that as we move along the section from west to east, the frequency package that we see thins out, suggesting a higher signal attenuation in the subsurface layers above that. Another feature here is the offset between the lines in the main reflector. We can see a gap in the continuity of the reflector, which suggests the presence of some sort of geological structure. There's another discontinuity up in here where the impedance contrast changes laterally along the line, and you can maybe see that it changes from a black color to a red color and a red color to a black color on either side of that line. This represents a normal layer impedance sequence to a reversed one along that line there, suggesting another geological structure. Also, there it is. Also important to note in this section is that we were not able to fully attenuate all of the noise, and there is still some residual secondary reflections down at the bottom. And these have remained visible. However, despite these noise areas, we're still left with a high resolution image of the subsurface that will become an important structural component of our entire data set.
Highway 131 is on the eastern side of the valley. It begins around 5 kilometers south of Steamboat and it extends further 8 kilometers. And here we can see that our reflectors are very well defined on either end of the seismic line, but are a lot less so in the middle. So this part of the seismic line goes through a thick deposit of glacial gravel, and we suspect that this may be causing our signals here to attenuate a lot faster. However, we can still see this general trend of south dipping reflectors, which we can use to understand our the regional geology.
Sweet. So what can we do now that we've processed all the data? Well, we can start doing our interpretations. For this project, we use Petrel software. We were able to take our 3 2D survey lines and make our own sort of 3D map out of it. Point in case, we started with Root County number 14, added on Root County Road 22, and then lastly, Highway 131. All this together allowed us to make our own sort of 3D model that we can do interpretations on and make a more developed hypothesis on what's going on beneath the subsurface. So exactly, how do we do our interpretation? Well, first we'll look at County Road 14. For County Road 14, we can see all these different lines. When it comes to interpretation, there's 2 main factors that you want to look at. That is the different geologic layers, as well as the continuity and continuous lines within the layers. First off, though, we want to look at our different layers. And how do we do this? We look at these bright blue and bright red lines. What is that? These bright blue and bright red lines are something called polarity. When you have an acoustic wave that sends down under the subsurface, it has a velocity as well as the layer has a density. The product of these together is called your acoustic impedance. This acoustic impedance difference between your different layers is what causes these blue and red lines. So if you have a high impedance in one layer and then a low one above it, you'll get these red lines called peaks. If you have the opposite, where you have a low impedance layer with a high one on top, you'll get these blue layers, which are called troughs. Knowing this polarity difference is also very beneficial to knowing where our different layers are. Also with this, if you have a high impedance difference, you'll get much brighter layers versus something like this up here. And in addition to this, we don't just want to look at the layers, but we also want to look at the continuity and continuous lines in these layers. Put in case like this, we can see different breaks in our color where we go from a blue section to a red and a blue to a red here. This can indicate things such as faults. Faults are very important for our geologic interpretation as it causes offsets and different changes in our different layers. With the peaks and troughs, as well as our continuous layers, as well as our fault interpretations, we can make our own geologic models. Here we can see this is our north-south cross-section of County Road 14. You can see that breaks will cause those different fault line layers. One of the things that are important about these faults is you have the different layers that offset each other. One pushes up, one pushes down. And this can be interpreted from our figures. So next we'll look at County Road 22. We can see that same peak and trough layer, and notice our different geologic layers, as well as different splits in our continuity, indicating that we might have some faulting, as well as our different layers. Lastly, we look at 131, where we can once again see those same peaks and troughs, impedance differences, as well as our different faulting with our discontinuous layers, and then we can make our own geologic models of those. From here, we can take our 3D grid, as well as our own interpretations, and make our own 3D model. This is our basement map. This is our initial map. You can see those cut throughs are where we define our faults, as well as you can see the different heights, elevation depths of our layers.
Great. So from that 3D model, we're able to make a holistic geologic interpretation of what's kind of going on in this area. So just a reminder from earlier, our initial hypothesis was this 4 distinct layer, but after doing our interpretation, we actually discovered that it is a 5-layer model with a fault running through the first 3 layers. So the first layer is going to be our crystalline basement rock. This layer has been identified based off its high seismic velocity and strong reflectivity. Overlying that is going to be an upper brown spark formation, and then above that is going to be a younger brown spark formation.
So we have a fault hypothesized running through these 3 layers Following that fault displacement, we have this glacial alluvial layer. So this is going to be gravel that was deposited by glaciation, like I was talking about. This was probably from the most recent glaciation event, which was 18,000 to 12,000 years ago. And as you can see, this unit kind of thickens to the south, and what we're expecting that's from is our fault leaves an area, an accommodation in the ground, kind of a low point, and then that gravel comes in and it fills in that spot and leaves the surface somewhat horizontal. And then after that, our fifth layer is going to be more of an alluvial flow. So the Yampa River probably established its course within this valley following the deglaciation. So the uppermost alluvial unit here represents the ongoing deposition from the Yampa River itself.
So one of the most significant outcomes of our work is the cautious identification and timing of a fault cutting through the Yampa Basin. The fault itself was identified during our interpretation work in Petrel, where, as Alex mentioned, we noticed a consistent offset in the subsurface horizons across our seismic sections.
Just a quick note here, we're interpreting this as a normal fault. What that means is we have our fault structure here. The thing below the angle of it is the footwall. The piece above it is the hanging wall, and the hanging wall falls down, which means it's a normal fault. And we can see those offsets here where this layer drops down, this layer drops down.
We also were able to determine the timing of this faulting using the principle of original horizontality, which basically states that the sedimentary layers are deposited horizontally parallel to the Earth's surface, and then any deviation from that original geometry is a direct evidence of post-depositional deformation. So we can kind of see that in this figure here, where on the west end, all of these layers are kind of the same thickness, and they run generally parallel to the surface. Well, over here on our east side, we see a lot of like dipping and moving up, which indicates our faulting. Now, you may be wondering, our glacial basement also kind of does that. Why do we not interpret faulting there? It is because that those layers have to fill in that accommodation, but we do not see that offset that we do here in our glacial units, so we do not interpret faulting there. And then while we're missing seismic lines to further our interpretation, the presence of the Yampa River also contributes to our hypothesis of faulting. Rivers are known to incise along fault-weakened rock zones, and the linear trajectory of the Yampa River parallel to Route County Road 14 suggests structural control on its drainage paths. And then considering the horizontality patterns, the glacial history, the presence of this river, and then our seismic interpretations, we're cautiously interpreting a fault in this region.
So the most prominent takeaway from this project is that identification of subsurface faulting. It's really significant because this faulting has not been previously mapped here. That alone changes how we interpret the geologic evolution of the Yampa River Basin and the Steamboat Springs area. This also has more practical implications. So fault structures can play a role in when, where, and how springs emerge in the Steamboat area. So understanding the fault structures helps us understand the springs. So all this together really highlights how much the Steamboat Springs area has yet to reveal and why continued investigation here is definitely worthwhile.
So there were a lot of things that we think could have added to the project that the limitations of field camp just wouldn't have allowed. One thing we would have liked is that to get a more holistic picture of the subsurface layering and faulting, we would have wanted more seismic lines in the region. In particular, we would have liked to extend County Road 14 down here further south. This would allow us to compare it with the data from the southern end of County Road 131. And this way, we could see if the structure changes across the basin or stays the same. We also would have liked more east-west lines connecting the two lines. This way, we could have better constrained the fault that we suspect the Yampa River is following, as well as improved the 3D aspect of our model. Having more lines that connect our main north-south lines at 14 and 131 would potentially identify new geologic structures.
Additionally, we'd also like to refine our processing workflow and experiment with new methods that time limitations just couldn't allow for. We needed to provide our interpretation team with reasonable quality and usable interpretable sections within just a few days, and there were lots of things that we wanted to try along the way, but just had too tight of a project timeline to do so. One example of this is our migration algorithms. For just a single step, this workflow has a huge impact on what our images look like and how interpretable they are. There are a wide variety of migration algorithms and parameters that can be tweaked to get vastly different results. An example of that is here, where we can see these two migrations. These are both of County Road 22, and you can see that they both show different levels of resolution, clarity, and number of features that can be seen on those. And that demonstrates just how big this processing step is on the whole of the image. Being able to find more optimal migration parameters and models for each line would make our sections much more interpretable and allow us to make a much more detailed interpretation.
This time constraint also applies to our petrel modeling. One of the best things about petrel is you're able to make multiple interpretations of the same figure. So in a real processing environment, we might take more than 2 weeks to make a single model or a single interpretation. We may take up to 4 weeks, maybe a little more, to make multiple interpretations of the same model. With this, we can get multiple different conclusions as well as overlap those conclusions to make the best possible result for our 3D and 2D figures.
And we also know that several other seismic lines have been shot in the area from previous field cams. We know of 3 to the west of our data that were shot in 2025 and 2023, as well as 2 more from 2024 that are more to the northwest of town. We didn't have the time to incorporate these beyond just a brief comparison, but we think they could be used to characterize the geology of a much wider area and potentially enhance our existing interpretations.
Finally, we'd like to give some special thanks to a few people. We did this project in 2 weeks and it wouldn't have happened without the help from so many people. So we want to thank GTI, Dawson Geophysics, and Todd for providing and managing all of our equipment. We also want to give a big thank you to Bob, Reza, and Ryan for spending hours with us one-on-one, helping us come up with these interpretations and process our data. And a thank you to all other faculty and staff on the screen for their feedback and evaluations. Thank you all for coming here. Thank you for listening to our presentation. We're happy to answer any questions now.
Don't be shy, audience.
Sort of Dr. Bob.
So I'm curious about your thickness map of the Browns Park or the overlying glacial material. I think I saw
Like this one or our hand-drawn map?
well, let's look at the hand-drawn one. That's hand-drawn. Where's the thickness map there? So let's go back to the digital.
Okay.
So the question is, are those meters or feet? What are the numbers on the?
Our depth is in meters. They're on the far left. We also have a depth below our surface right here at scale, but less applicable here.
So it'd be interesting to look at a plan view map of your interpreted thickness and see if it should show the fault pattern, right? I mean, because it should thicken up against the faults. The center should thicken up against the faults.
Yeah, one of the largest constraints I would say about our modeling software is first off, we're using multiple 2D surveys. So when we try to apply our faults to our whole figure, it doesn't necessarily work as well as if we just had a 3D survey. We are somewhat limited by our, I guess, applications that we're using, which is why in our own personal interpretations, we tried to show what we could about the different thicknesses. That answer.
What would happen if you used a piece of graph paper?
I could draw it differently.
Yeah, you could put the numbers on a piece of graph paper and then you could convert them yourselves. It's just an idea.
Thank you.
I have a question from online. Did you consider using gravity surveys or other technologies to corroborate the faulting?
Yeah, so actually along State Highway 131, there was a gravity survey along that. Unfortunately, the GPS data was really hard to access for that, so it was hard to get actually where that was. And then the spacing was just too coarse for us to be able to actually interpret anything from that. But it definitely is something that if you had more time, could be helpful to interpret the faulting.
So do you think you've got one fault or two faults? How many faults do you have?
Based on our initial model, we thought we had a main east-west fault that followed, or I guess fault that runs north to south, but it's across our east-west line that follows our Yampa River Valley, or I guess the Yampa River. Also in our north to south grid, we had a large accommodation area that we thought could have been from faulting that caused that kind of dip down of that accommodation area, which is what we see in that top grid. We weren't 100% confident, or I guess 100% confident. This is our baseline, I guess our final interpretation, But with further interpretation time within our software, as well as maybe some more refined data, we can really solidify more information about what it may look like.
Thank you. We'll move on to the next one. We'll have some time for questions at the end as well. Right. Now that we've had a regional overview of the Yampa Basin, we're going to focus in a little bit more on some of the Travertine deposits with other geophysical methods.
Hello, everyone. My name is Emily Pearson, and along with Raquel Dickinson and Lily True Flores, we worked on characterizing Travertine deposits with near-surface seismic refraction at Howelson Hill, Critter Spring, and Lithia Spring in Steamboat Springs, Colorado. And before we get into the surveys done and the seismic refraction method, I'm going to start with some geology background just to go through what Travertine is, why it's useful to map, and what is already known about Travertine at the survey sites we visited. So to start, Travertine is a form of limestone made mostly of calcium carbonate and forms when mineral-rich hydrothermal spring water reaches the surface. As the water rises and flows away from the spring vents, pressure and temperature decrease and the dissolved carbon dioxide degasses from the water, causing the calcium carbonate to precipitate. This builds Travertine deposits at the surface around the spring vents and outflow paths, which acts as a physical record of where spring water reached the surface and where that water flowed after discharge. Because Travertine forms at or near the surface, deposits found at depth can suggest former ground surface where spring water once discharged or flowed, and such deposits may have been buried, reworked, or covered by slope processes after its initial formation. And additionally, mapping Travertine deposits can provide information about past spring locations, flow paths, and hydrothermal activity, which can support the protection and management of hydrothermal spring landscapes, such as the Steamboat Springs area. And to start with our survey areas and some background surface geology, Travertine is known to exist in Steamboat Springs, but the existing information is incomplete and uneven across our survey areas. On the right here is a map of the surface geology of the Steamboat Springs area from 1991, and we can see that our Howelson Hill survey area overlaps with a Travertine deposit mapped. However, the Lithia Spring and Critter Spring survey area does not, and instead overlaps with a landslide deposit. This difference is important because the surface mapping of Travertine gives us the stronger evidence for subsurface Travertine in our interpretations. And for Lithia and Critter Spring, even though the Travertine is not mapped at the surface, it does not conclude that it does not exist in the subsurface. And in our Howelson Hill area, in addition to having the surface geology mapped, prior test borehole drilling by Yet and Associates for a geotechnical project provides some local subsurface information shown by the lithology diagram of a borehole in the survey area, which shows evidence of possible Travertine layers and Travertine cement gravels at various depths. And essentially, we can use this as geologic context for interpreting these our Howelson Hill results. And even though the test borehole locations do not line up exactly with where we surveyed and do not provide exact ground truth, they can still be used as reference and information that Travertine does exist here, the subsurface. And then moving on to our Lithia Spring and Critter Spring area, it's important to note that Critter Spring is not an officially mapped spring, but it was nicknamed by Audrey Walker at Colorado Mountain College, which we thank her for pointing it out to us, which led us to this type of project. And the survey area here is less constrained because we don't have any detailed subsurface information comparable to the Howelson Hill borehole lithology. In addition, we don't have the the surface geology of Travertine mapped here. However, both of these are active mineral springs, which make Travertine deposition geologically plausible, and we additionally observed potential Travertine at the surface during data collection.
So here I have some of our survey lines. We are analyzing a total of 4 survey lines for this analysis. Over here, we have 2 survey lines that are on Howison Hill, and we have 2 in the Lithia-Critter Springs area. For future reference, this survey line will be referred to as the Northwest Howison Hill survey. For all my students that might be thinking about it in terms of group, that was group 2 survey. This was group 3, and we'll be referring to it as the Southeast Howison Hill survey. So zooming in on Howison Hill, we can see that the geometry of these surveys look a little bit different. So the Northwest Howison Hill survey is 144 meters long with 72 geophones at 2 meter spacing. There were a total of 9 shots done at this location. The Southeast Howison Hill survey is 94 meters long, done with 47 geophones at 2 meter spacing, with a total of 16 shots, which is the densest of all the locations. Now zooming in on Critter and Lithia Springs, the Critter Springs survey is 144 meters long as well, with 72 geophones and 2 meter spacing, with a total of 11 shots taken at 9 shot locations. The Lithia Springs survey is 48 meters long, making it the shortest of all of our surveys, with 24 geophones at 2 meter spacing, and a total of 10 shots were taken at this location. Before we dive into what each of these survey lines produced, let's talk a little bit about how seismic refraction works. So here we have a diagram showing a 1D survey line. All of our surveys were one-dimensional, which basically just means done in a straight line. In a survey line, there will be an array of geophones shown here in this magenta color. These essentially measure vibrations in the ground according to the ground's acoustic impedance. To create the vibration for these surveys, we use a hammer on a metal plate, which was moved to various locations for the different shots. The acoustic waves from the impact manifest in 3 main waves. First, you'll get your surface waves, which are shown here in red. These often are the loudest in your survey and are not really relevant for this type of analysis. You'll also get your direct wave, which is shown here in purple going across the surface. What we're really looking for, though, is our refracted wave, which is shown here in green. What essentially happens with the refracted wave is that it goes down into the surface until it reaches a higher velocity layer. It'll then trace along that layer for some time before coming back up and meeting our geophones later on, which is why survey length matters, because at short survey lengths, we might not see that refracted wave come back up. The data we're going to see coming from our seismic refraction is going to look something like this. We call this a wiggle plot. With distance on the x-axis and time on the y, we can get a wiggle for each geophone location. If you look closely, you can start to see how the wiggles are sort of traveling across. So we can connect those wiggles, kind of like connect the dots to see our different types of waves. Down here is going to be all surface waves. We don't really care about those for a refraction analysis. You'll also get your direct wave, which is also irrelevant to this type of analysis. What we really want to see are these first arrivals where the refractive wave is going to be. So let's talk a little bit about how we pick those first arrivals. This is what a real shot from real data actually looks like. This is the 16th shot done on the southeast survey of Howison Hill, and the shot location is noted with this little hammer illustration. Just a visual analysis looking at this shot, the only thing that stood out to me is the line noted in blue, which is just the speed of sound in the air, essentially the sound of the hammer hitting the plate. And I don't really want to see that. So we're going to filter the data. To decide bandpass filters, we plotted the frequency spectrum for each shot to see where the amplitudes are the highest. In this shot, we can see that under 40 hertz is where we see the largest amplitudes. And so the bandpass filter selected for this site was between 5 and 40 hertz. This analysis was done for every site, and what we decided was that both Howison Hill surveys would have the 5 to 40 hertz along with Critter Springs, and Lithia Springs had a filter of 20 to 80 hertz. This is what it looks like when you actually filter that data. Doesn't that look so much better? We can start to see actual lines, but let's zoom in a little bit to get those first picks. Upping the gain as well so that we can see those amplitudes a bit bigger. We want to look for a nice smooth line coming from the source location, which is over here. The first picks are noted in red. Now we can plot those first arrival times and decide what we think about our layers.
When you look at clusters of these data, my first thought is I see a line going here, and I see a line coming here. So I'm going to plot best fit lines for that. The slope of that best fit line is going to be in inverse of velocity. It's going to be seconds per meter. If you take the inverse of that, you get the velocity of those layers. We can then also calculate depth of the layers by using the time of interception, which is going to be about here in this case, and then use this depth equation. This was done for every single shot in order to validate our inversion models. Speaking of inversion models, here's kind of what they look like. Specifically, we were performing 2D velocity inversions, showing velocity changes laterally and with depth. We were able to import topography files as well to help the inversion not be skewed by slopes on the surface. Each inversion was done with its own unique set of parameters based on our 2-layer models and general geologic expectations.
All right, so before we get into our inversion interpretations, I would like to note that Travertine's velocity, it ranges between 2,000 and 4,000 meters per second. So within our inversions, we are typically trying to see within that range, our anomalies that are within that range. So for Northwest Hellison Hill, we see this anomaly right here. It's about 3,300 meters per second at depths of 16 meters. This could be Travertine, considering that the survey line is located right next to the Travertine deposit on the geologic map. And so with as we look here in this inversion, we can see the ray paths. It sort of starts to flatten out right here. And that's because the ray paths are trying to trace the fastest layer velocity there is, meaning that our anomalies are in that region. So with each inversion was validated with shot gather analysis for each shot to confirm that the depths and velocities the inversions were producing were consistent with the manual calculations. For this site, we see the sample shot gather analysis that the depth is greater on the left side than is on the right shot, which is consistent with our inversions. Now we get into our southeast Hellison Hill. We see this kind of low velocity area and then high velocity area. This follows with our survey lines because for this survey line, it was plotted right on top of where the Travertine deposit is. So we are more likely to see Travertine within our inversions, which this could possibly be. Again, we see our flattening here, meaning our Travertine deposit could be in that general area. All right, so for Critter Springs, we see this little anomaly here at the subsurface. This is because of a poorly coupled geophone. This means that the geophone wasn't properly placed into the ground. And the reason for this was because there was a giant rock deposit on the subsurface, which we later observed could be Travertine, meaning we are still looking at Travertine within this area, even though that the survey was conducted upon the landslide deposit. So for here, we kind of see that high velocity concentration of 2,850 meters per second, meaning Travertine could still be here. Also, we see this kind of split between the rays, meaning that our geometry of our deposit could be in this general area. All right, so looking at the shot gather analysis for this site, we are seeing very different velocities for the 2 layers from each shot, along with the 58% error in the inversion model, which gives us low confidence in the Critter Springs model overall. We do see that the shot gather analysis with the general depth of the high velocity layer is about 12 meters, which is consistent with the inversion, but we are hesitant to draw any real conclusions with this site. Now, our last location is Lithia Springs. We see this anomaly here. It's very similar to Hellison Hill. Again, since our survey was located on landslide deposits, we can't infer that this is Travertine specifically. So yeah, and here are our ray paths. Again, it's following along that anomaly right there. Now for significance with our conclusions, we can identify and analyze higher velocity locations and make inferences about Travertine deposits, as well as identify the relative geometry of the distant velocity layers from our inversions. But our our conclusions come with limitations. Near-surface seismic cannot identify travertine alone. There needs to be other geophysical methods to really support the evidence that there is travertine there, as well as possible geology observations. All of our surveys were 1D lines, which restricted our surface area covered, and our lines were relatively short, which limits our refracted wave returns. Now, onto our future work. We want to support our future work and our inferences with core samples, resistivity data, more near-surface seismic data, but with different parameters and more GPR data. We would like to acknowledge all these people who are up here. Without them, our project would not be made, would not be done. So, are there any questions?
I think we have time for one question as we flip over to the next group.
What is there alternative interpretation to your high velocity?
I think that we would suspect probably shale as a higher velocity anomaly that would be likely to see. Also in the Hallison Hill area, some of the core samples had stated possible travertine deposits or just possibly gravel in general. The thing is that the travertine we're going to be seeing is all going to be weathered, and so those velocities overlap with a lot of different types of rocks. So there's definitely other possibilities, but based on the geology and then how travertine forms, we expect that our higher velocity anomalies would likely be travertine.
Thank you. Now we're going to learn a little bit more about Lithia-Critter springs.
Good afternoon, everybody. Today we're going to be characterizing the Lithia-Critter spring area in Steamboat Springs. I'm Rory.
I'm Zoe. And I'm Anna.
So to give you guys a little context on what we'll be getting into today, we're going to start with an introduction and background on the area that we were working in. Then we're going to go into the methods we used, the results from those methods, our interpretations of those results, our future work recommendations, and then finally some concluding thoughts.
Just to give you guys a little bit of an introduction to spring systems, we're going to be talking a lot about travertine today. I know the last group introduced that, but it is calcium carbonate rock deposited by mineral-rich spring water. Research at Mammoth Hot Springs in Yellowstone has shown spring behavior controlled by travertine buildup, diverting spring pathways. And then understanding these spring systems can tell us a lot about the subsurface, as they are expressions of complex subsurface hydrology and geology. And while major geothermal systems such as Yellowstone are well studied, Steamboat Springs remains under research, making it a great learning opportunity.
Okay, so just to give you guys a little background on our survey, we are looking at Lithia-Critter springs, which are both in Steamboat, Colorado. They're about 126 meters apart. And whenever you look at them in person, you can see that they have a very similar color, smell, and opacity. So, which leads us to think that they're from the same source. The geologic setting of this area, the surface geology is dominated by landslide deposits. And under that, we believe there's Cretaceous sedimentary rock. And then there's travertine dominating the spring system.
So for our project, our objective is to determine the subsurface connections between Lithia and Critter Springs through identifying the travertine deposits. And we hypothesized that a single paleo spring conduit was blocked by travertine buildup, forcing fluids to bifurcate or split around that, which resulted in the two springs that we see now on the surface. For our approach, we use a combination of GPR, ERT, seismic, gravity, and geochemical analysis.
Yeah, so to give you guys a brief overview on the methods we used, we'll start with geochemical analysis, which was taken at Critter Springs, which is the cyan dot, as well as Lithia Springs, which is the dark purple dot over there. So for this, a water sample was taken from the active bubbling source because we wanted to look at the isotope composition of the water just to get an idea of if the springs might potentially be connected. Then GPR was also performed, which is this purplish pinkish grid area over here. GPR works by sending EM waves into the ground, which will then reflect off of boundaries between materials with different, with contrasting electromagnetic properties, and then that will be received by the GPR, and then we can analyze that data.
For near surface seismic, which is for on the Critter Springs line, this yellow dotted line here, as well as the Lithia Springs line, which is this yellow triangle line here, was executed using an 8-pound sledgehammer striking a steel plate. This sent seismic waves, P waves, into the ground, which then refracted across boundaries of layers with different acoustic impedances. Acoustic impedance is the multiplication of the layer velocity as well as the layer density, which was then received, and then that data was recorded by the geophones that we had set up along those lines there. For our ERT data, ERT works by sending an electrical current into the ground that measures voltage differences, which we can then use to map the electrical resistivity of the materials in the subsurface, and that's that blue line right there. And then finally, we conducted 2 gravity surveys. One was this red grid here, and the other was this green grid here. Gravity is important. Gravity works because mass distributions in the ground can be picked up by the gravitational force, which is influenced by the acceleration due to gravity. So for example, for our Travertine, which should be more dense than the surrounding soil, we should see a positive gravity anomaly. However, unfortunately, our gravity data proved to be inconclusive.
Okay, to get into some of our results, we have the global meteoric water line, which is this black line on this graph, which means water that has not come into contact with any kind of rock or any evaporation. And as you can see, the Lithia and the Critter Springs dots are off of that line, which means they have oxygen 18 changes in them. That means that the water went underground and interacted with rock in the exact same way because our oxygen 18 values are nearly identical. This is consistent with the idea that they have a shared source. The ion chemistry is also nearly identical, further supporting our shared source hypothesis.
So now getting back into the GPR results, again, here is our GPR survey relative to Critter and Lithia Springs. So for one of our slices here, this red line is what part of our survey grid that this radargram represents. We could see that the cyan dots are hyperbolic anomalies that are relative to dry and wet limestone, which was used as a proxy for Travertine due to their similar calcium carbonate contents. And then this green line here indicates a planar anomaly that demonstrates that the Travertine block that we are interpreting this anomaly to be spans multiple meters. We also have anomalies that are of lower EM wave velocities that could correspond to water saturated soil, like these purple dots here. Again, another planar anomaly. And what we believe the water saturated soil could indicate is the groundwater that is feeding the springs flowing around the Travertine block going towards each of those springs. After looking through all the radargrams through the survey grid that we have, it appears to be a central Travertine block in the middle here with 2 forks, 2 branches going towards Lithia Springs, a north and a south branch, as well as a potential branch going towards Critter Springs, and we'll get into those in a moment.
For our near surface seismic data, we had 2 survey lines. We have Critter line, which is on the west side, and the Paleo-Lithia line on the east side, closer to Lithia Springs. For the Paleo-Lithia line, we have several high velocity anomalies. The 2 showed in white circles we interpreted as Travertine. How does this work?
The green dot, yeah.
This one right here, we have also observed Travertine at the surface right above that, so we're fairly confident that that is in fact a Travertine block. And then we also have a high velocity anomaly deeper here, and we've interpreted this as shale. This inversion here has a 13.45 relative root mean squared error. Industry standard is 10%, so it's a little bit higher than that, but it works for our purposes. And then for our Critter near surface seismic line, we also have several high velocity anomalies circled in white. Again, we interpreted as Travertine, and again, lower or higher velocity at greater depth. This survey did have a wider receiver spacing as well as few shots and a lot of noise in the area due to electrical substation proximity and then power lines causing a lot of specifically 60 hertz noise. It also had a slightly higher error.
For our ERT survey, we wanted to go into a different direction. So instead of our hammer seismic and our GPR all kind of following the same line, we went more northwest. And we had a complete dipole-dipole survey and an incomplete Schlumberger survey. We did a joint inversion of the 2 and found that there was a highly resistive anomaly near the top. It's about 0 to 3 meters in depth and 15 to 55 meters across our 64-meter survey. There's lower resistivity zones within our high resistive anomaly that we will talk about in a second, but we wanted to compare our ERT and our GPR surveys. And so we found a line in our GPR that is as parallel as possible and as close as possible. And so as you can see, that hot pink line further east is almost right next to and parallel to the ERT line.
Yeah, so focusing on the eastern part of the GPR line relative to the ERT line, and then trying to find coincidence anomalies from both, we can definitely see that those lower resistivity anomalies that Anna pointed out just earlier, as well as the planar anomaly that is highly resistive in the ERT data, as well as this planar anomaly that can be seen in the GPR data here, line up, as well as these breaks in those anomalies, which makes sense because in the ERT data, we could see that that is less resistive as in more conductive, which aligns with the potential areas that were saturated soil in the surface of the area over here. And that would cause the radar waves from the GPR to attenuate quickly, which means we wouldn't be able to resolve the deeper potential anomalies there.
We also wanted to go into the depths of our surveys. So the GPR and the ERT line up in terms of depth. We wanted to make sure that the anomalies we're seeing with both of our different methods line up. And as you can see, they do. They also taper in the middle, which is further proving that they are seeing the same thing.
Comparing GPR and seismic results, we have sections from both GPR and near surface seismic at the Paleolithia line. We can see that those surveys pretty much line up exactly. Circled in purple is that close to the surface section of Travertine, and it appears in both the seismic or both high velocity anomaly and in the GPR anomaly, corroborating the presence of a Travertine deposit as well as our surface observation.
Another anomaly that we're interpreting as Travertine in the seismic data here, that's represented by the white circle on the line over there, cannot be seen through the GPR data. Once again, believed to be due to the water in the surface that is attenuating the radar waves quickly. So we're unable to resolve the deeper structure and potential Travertine anomaly that should be around here that we do see up there. So we're less confident in that one as opposed to the Travertine anomaly we're seeing here and here. So now for our overall interpretations, we broke it up into three categories. We have what we believe we are highly confident about is that central Travertine deposit right here. That's corroborated by our GPR data, our ERT data, and our near surface seismic data, as well as surface observations of the area where Travertine was seen all over the ground. We are moderately confident about the two branches extending towards Lithia Springs, with the northern branch being corroborated through GPR as well as the seismic data. However, the southern branch is only seen through the GPR data, so we're less confident about that. And then finally, we are not incredibly confident about a Travertine branch extending towards Critter Springs, as we have a lack of data and survey data in this area here, as well as the GPR data in this area attenuating quickly due to the water saturated soil.
So in terms of future work for GPR, we want to go back to the area with a finer grid and a larger coverage going closer to both Critter Springs and Lithia Springs. And we additionally want more frequencies. For ERT, we want to do a Schlumberger array that can go deeper. So mapping out the depth of the Travertine would be possible, and making a grid of the ERT data so that we can get closer to like a 3D model with that method. And then for near surface seismic, we want to keep the same spacing of nodes as we had on the Paleolithia line, with the same source locations, but longer surveys so that we can see further and corroborate any of our further GPR data. With gravity, we just don't think it would be necessary because of the large survey grid and the finer measurements we'd have to take.
Conclusions from this project. So from geochemical analysis, we can say with a high degree of certainty that Lithia and Critter Springs originate from the same source. GPR, near surface seismic, and ERT all show a large Travertine deposit existing between the two springs. We've interpreted this as a paleo spring blocked by Travertine that forced the system to migrate and bifurcate. We also mapped Travertine branches representing the historic spring water flow around the area, and we believe the deposit extends towards Critter Spring, meaning both springs could share a common subsurface origin.
We have a lot of people to thank for our project. We would not have been able to do it alone. So big hand to them from us at least. And thank you very much.
Couple minutes for questions.
Yep.
So it seems like your travertine block is largely concentrated toward Lithia Springs. Do you think there's a reason why Critter and Lithia are so far spaced apart, with your travertine block being mostly located toward the Lithia section?
We don't have any methods closer to Critter Springs, so it could be further that way. We just don't really know yet.
The block could extend, at least with the GPR data, we could see that there are some some planar anomalies extending in this direction that could be a continuation of the travertine block. A lot of the area had saturated soil, so some of the GPR waves attenuated, kind of like we mentioned earlier. So more data needs to be collected, essentially.
Is your interest in travertine as a target mostly because it helps you put together the history, or is there another reason to be so focused on travertine?
Travertine is our main target because as the spring water flows like through the subsurface, it deposits it, right? And so by tracking where the groundwater flows, we can see, or by tracking the travertine, we can see where the water has deposited the calcium carbonate. So we have an idea of where the spring conduit might be as it comes up to the surface, and then as it branches out and deposits it. Yeah, we can see the like historic travel of the spring flow. Yeah, Ryan. I would imagine a very long time. Yeah.
Said that you had high attenuation of the radar signal because the soil was water saturated. Is water saturated soil always a high attenuator of radar? And if not, under what conditions does that statement hold true?
Yeah, so that would depend based on the mineral content and the conductivity of the groundwater. So if it's very fresh water, it won't it won't be very conductive, which means the radar waves will be able to penetrate through without losing energy as they travel through. But because we're in such a mineral dense area and the spring water is very concentrated with the minerals, as we can see from our geochemical analysis, it's going to cause the radar waves to attenuate very quickly. But if it was like pure fresh water, then the GPR would be able to see through it.
Questions?
It was either you or the other group who were best looking at Lithia Spring or Critter Spring, indicated that maybe in the bottom of your refraction section, the high velocity indicate like shale bedrock or something. And is there evidence from your electrical resistivity section that supports that, or do you have any comment on that related to your other
Because of the incompletion of our Schlumberger array, I would say that we're mostly confident about what we can see at the surface rather than what would be like the deeper shale area that we're interpreting from our seismic data. So for our future work, doing a Schlumberger survey where we can see deeper, I think it would be ideal for answering that question.
Our Schlumberger array didn't even get 50% of the way done. So we really think there would be a lot more data if we could have a complete one.
Yeah, that interpretation as shale is mostly based off of just like literature in the area that says that Cretaceous sedimentary rock is there.
Thank you.
Right, continuing on and looking at some shallow subsurface features, we'll be looking at a favorite of Geophysics Field Camp, which is the Sulphur Cave system in Steamboat Springs.
Hello, my name is Erica Mabius.
I'm Anna Williams. I'm Chandler Bergstrom.
And for our project, we looked at GPR for mapping near surface caves. So why do we even need to study caves? Caves can act as a portal into the past, revealing unique, isolated, and sometimes even prehistoric ecosystems that have been preserved for thousands or even millions of years. However, as a result of their isolated nature, caves can prove difficult to study and learn from, due to their location, the harm that intruding upon the cave can cause, and the danger that it can put the researchers in. For that reason, it is important to gain an understanding of these systems using non-intrusive methods.
So to set the stage, we are looking at Sulphur Cave and Spring on Howison Hill in Steamboat Springs, Colorado.
It's right by Magic Carpet, which you can see on the map, which is a ski lift. It's a unique cave system formed by sulfuric acid speleogenesis. The cave is actively being dissolved by sulfuric acid, making it hazardous to explore. A research team from Mines did explore it in 2023. They were able to study the unique species of life called bloodworms, which are over there, which can only be found in that cave. They also got it designated as a natural national landmark, and they were able to map the cave's extent from the inside, providing a good baseline for us and our survey process. Because manned exploration is dangerous and not always feasible, we need another way to study it without going inside the cave.
So we looked into GPR in order to do so. So GPR stands for ground penetrating radar, and it works by sending out a radio wave signal into the subsurface. When that radio signal encounters an object or layer with contrasting electromagnetic properties, some of that energy gets reflected back up the subsurface. Back up, where the GPR will measure the amplitude of the reflection as well as the two-way travel time, producing a GPR trace. And so by lining up these GPR traces over distance, we can get a good idea of what the subsurface looks like. Some important considerations for a GPR survey are your frequency content, which you define. So longer frequencies, like the 70 megahertz antenna showed here, can see deeper. However, it would likely have less resolution than the 300 megahertz antenna. In terms of surface geometry, it's important to think about your area, your line spacing, and your trace spacing, as these define both your spatial resolution and also your spatial extent that the data is taken over. Our goal for this project was to determine the most optimal survey parameters best suited for mapping near-surface caves. There were 3 surveys over the past 3 years, 3 GPR surveys over the past 3 years over Sulphur Cave. One in 2024, 2025, and 2026, each with differing frequencies and as well as grade parameters. Additionally, in 2023, there was that expedition into the cave where they mapped the cave extent, which is shown by this black outline in the image.
So how do we go about using the data from these previous surveys and making it into something that's actually interpretable? For our workflow, we decided to use Geologic, which is a GPR software specifically made for this purpose. So we begin by uploading our raw survey data onto Geologic with a small constant gain, just so we can see any of the traces. We then continue to remove the background noise and de-wow all of the data to remove the low frequency noise as well. We apply corrections to ensure temporal and spatial accuracy. And to finish off, we boost the desired time ranges, which in this case is around 150 nanoseconds, which was estimated via the 2023 cave exploration.
So after processing the data, we estimated the maximum depth that each of the frequencies could see to. To summarize, the 300 megahertz data saw the shallowest, but it did have the highest resolution, as was expected. The arrows are wrong. The 70 megahertz data actually showed us the deepest, down to 8.4 meters, which is a little different than what we expected, because typically the longer frequency would see deeper. But we think that's due to survey conditions as well as subsurface water content. In addition to comparing the depths, we also looked at specific traces across the frequencies over a specific extent of the cave. So each of these lines are showing the lines that we're looking at. So these 2 cross sections are from the 2024 data, the 100 megahertz and the 50 megahertz, denoted by the orange and purple lines seen in the inset at the top. You can see that right around 150 nanoseconds, the signal starts to get pretty attenuated, which is likely due to water content in the subsurface.
Adding in these two at the bottom, these are from the 2026 survey of the 70 megahertz and 300 megahertz, which are seen in the red line there. What's not pictured here is the 50 megahertz data from the 2025 survey, and that's due to the low resolution from the chosen trace spacing. To point out a couple of things, from the 2023 mapped cave extent, we know that the roof of the cave should be right around 150 nanoseconds. However, in all of the GPR traces, you see a pretty high signal above that line, and especially right around 100 nanoseconds. So based off of this, we believe that our previous thought depth of the cave is actually a little bit shallower than as expected. We also took a look at the lateral extent of the cave system. So these dashed blue lines are indicating the cave walls. So W shows the western portion, western cave wall, and then E shows the east cave wall. So right in the middle here should be where our cave is located, but we can see high reflections on the eastern portion of the traces, indicating that there's potentially unmapped cave extent.
To add on to the frequency comparison, we also have made an interpolated map of a bird's eye view of the cave with the frequency data. And each one of these 8 figures are composed of various 1 meter thick slices from the depths of 2 to 8 meters layered on top of one another with pretty high transparency. So on the left, you can clearly see a distinction near the cave, which is marked by the orange circle, of extreme reflective values that are also marked by the yellow and greenish values that are likely indicative of the void space from the cave. And then on the right, with the migrated data, you see significantly less extreme values as they have been condensed into smaller points. But this is actually almost preferable because you can see where the geologic and geometric representation of the reflective points are more accurately in the migrated data than in the unmigrated data. And then on top of that, I then proceeded to stack each one of the frequencies on top of one another to see what features get amplified and which ones get dampened. And on the unmigrated section, we can see an especially prevalent anomaly running coincident with the magic carpet that is almost interfering with the data that we were trying to collect of the cave. But once we move to the migrated data, it kind of separates itself. And this allows us to get a very rough geometric sketch of where we believe the cave to be and where we believe the anomaly to be located. And then when we compare that with the previously mapped cave extent from 2023, we can see that some of the area lines up. However, on the eastern side, there is a pretty large extent that we hypothesize is just unmapped due to the limitations of being able to access it with manpower.
So what subsurface model can we use to explain the anomalous zone? One answer to that would be forward modeling. Forward modeling is crucial in geophysical processing. It's a process of using models that simulates a certain system to predict data behavior. In a forward modeling context, we don't process real-world data collected in the field, and instead we are using laws of physics and nature to mathematically simulate what a GPR antenna should record when dragged across a specific environment. We use GPR Max, which is a software suited for forward modeling. The flowchart on the left here shows the general process. Basically, you start with real data and a GPR Max synthetic model. Both show anomalies and subsurface information. And when you compare them, if they match, that means the target is mapped. And if not, the model needs to be reworked. So this is our forward model of the cave and the anomaly. It simulates 70 megahertz GPR profile over the 25-meter grid. The cave is the first big blue upside down U right here. It represents the cave air void. Because air pockets in the surrounding material differ greatly, it creates a wide arched hyperbola with an inverted wave phase peaking at 68 nanoseconds. We also know that the floor of the cave is running water, so there's a thin acidic water floor under the big blue hyperbola right there. The anomalous zone, which is outlined in black in the upper right corner, we hypothesized it to be a relatively small metal pipe. It shows a compact localized pipeline on our forward model And there's wave ringing of the energy bouncing off the hypothesized metallic material, which you can see underneath. This plot demonstrates the type of hyperbolic signature each target, both the cave and the pipe, would make crossing realistic travertine bedrock material, which we know to be in the subsurface of that area. So moving forward, we can now use what we learned from processing and our forward model to create an optimal survey design. Some important criteria for mapping is if it will reach the depth that we need, and if it can resolve both the vertical and lateral extent of the cave. So to ensure that the criteria is reached, we recommend doing a multiple offset, which is a surveying technique where data is collected using a transmitter and multiple receivers at varying distances. This allows for data to be stacked and improve signal to noise ratios. Megahertz for depth and clarity, which is what we use in the 2026 survey design. We also recommend a line spacing of 0.5 meters and a trace spacing of 10 centimeters for distinguished images. For the grid, we recommend getting as close to this fenced off area as possible because we don't have any GPR data from mines that is covered by that area.
So to summarize, we use Sulphur Cave as a case study for determining the most optimal GPR parameters for mapping near surface caves. We determined that the 70 megahertz and 300 megahertz antennas were well suited our needs for mapping caves. We did find that the GPR data collected over the past 3 years was somewhat inconsistent with the mapped cave extent from the 2023 expedition, especially in the southern and eastern portions of the cave system. And we also looked into the large anomaly running coincident to the magic carpet and used forward modeling to support our hypothesis that it's a man-made object like a pipe.
We wanted to thank all of these people. We really couldn't have done anything without all of the people who helped set up field session and all the people who helped us interpret data. So really thank you.
We have a few minutes for questions.
So do I gather that you hypothesize there's a cave underneath the magic carpet?
Oh my gosh.
But that you've got an anomaly running parallel to the magic carpet. Is that a cave?
So we mainly hypothesized because of the just sheer amount of consistent ringing that it was causing across multiple frequencies, but specifically the 70 megahertz frequency, that it's probably a pipe of some sort, just a small metal pipe.
So not the cave extent going into the.
You have some online questions. I don't believe that there are any underground utilities in this area. And the magic carpet was installed above ground, so do you, so that it would not interfere the cave system, do you have any other possibilities that aren't like a pipe?
Not necessarily. We thought about it that maybe it would be just an extent of the cave, but because of that cave wall, we know that that's not true. So the pipe was kind of our hypothesis.
It could also be an extent of the groundwater flow since there's so much water running through the cave from the people who we've talked to that were actually in the cave. We know that all of the water does have to be going somewhere, so it could be some type of underwater stream, and that's just where it all co-locates. Yes.
There's another question online. If we were to try to map the cave fully, like a high resolution 3D map, I assume GPR is not enough, right? What combinations of instruments would get us an accurate full map, assuming infinite resources?
Oh.
Clearly from a graduate student.
Well, so there have been other surveys conducted at Sulphur Cave, including resistivity. There was some gravity surveys. I think those were the main ones. I think resistivity would be the most helpful, but you would need a lot of time in order to set up the,
survey.
Yeah, the grid parameters that would be needed to define the cave extent because it is so small.
Gravity potentially, but it wouldn't be refined enough really to get into a solid 3D map, unfortunately.
What's difficult about using the GPR over Sulphur Cave is it's a sulfuric cave. And so there's a lot of water running through it and a lot of acidic water running through it, which is also contributing to signal attenuation, and it might interfere with some of our interpretations.
Thank you very much. Right, moving from cave systems to mines from 100+ years ago.
Exactly.
Hello, everyone. My name is Molly Billhartz.
I'm Samantha Lopez.
I'm Tessa Murphy, and this is our project. So why do we even care about mine shafts? Well, historic mine shafts may be unstable and collapse, resulting in sinkholes that cause public safety issues. And you could hypothetically fall into one of these sinkholes, and that would be no good, would it?
This is our survey site. The Onyx mine, which we were trying to map using a multi-geophysical technique approach, is atop Holliston Hill, which is just south of Steamboat Springs, Colorado. And here you can see one of our classmates, Zach, pulling up the 70 and 300 megahertz GPR sled up the hill to our survey area while collecting data on the way up.
All right, so here's some site info or background about the geometry and geology of the mine shaft. And here in figure 1, we can see a historic map from 1904. And basically you can see right here, it says shaft, and that's also on top of our survey area where we have a known mine shaft we saw with our eyes. And then figure 2 also shows us more of the geometry of the actual mine shaft. It says that it's gonna be around 200 feet into the mountain, as well as no less than 6 foot square tunnel. And then it also says in that article that it'll be packed in with clay in the walls. And then finally in figure 3, it says that we're gonna have, or for our geology, we're gonna have a layer of soil on top of our layer of clay.
So when thinking about the methods that we want to use when approaching this mine shaft problem, we considered gravity as a really good method because it is controlled by the distribution of mass in the subsurface. Essentially, more mass has a weaker a stronger gravitational force, and less mass has a weaker gravitational force. So essentially, gravimeters measure the local gravitational acceleration of the Earth, and when we are considering an air-filled void, the gravitational acceleration measurement atop that mine shaft will be less than the surrounding gravitational acceleration measurements. This would result in a local negative gravity anomaly. This figure over here represents that. We see the negative gravity anomaly at the same location along the line where the void is placed.
Another method that we chose to use is GPR, which is ground penetrating radar. The EM signals, the electromagnetic signals, reach a boundary between the rock and an air-filled void, like a mine shaft. There is a strong impedance contrast, and this is due to the rock and the air's different dielectric permittivity properties, which produces a distinct reflector at that boundary. And this radargram here in figure 6 is an example of distinct reflectors that we could expect to see when we're hitting boundaries with different dielectric properties. And here is a figure showing our survey design. The base map is elevation of the area, and this is atop Holliston Hill. As you can see on the right-hand side, there is a large drop in elevation, which was a cliff just to the side of our site, and the star up here is a mine shaft opening that we actually located around our site, and the green line is the projected 200-foot/60-meter extent of the mine shaft into the side of the hill. And the blue dots represent our gravity stations, and we ran a 29-meter gravity line with 1 meter spacing between our gravimeters, and then we had denser half-meter spacing above our projected mine from stations 12 to 16. Our purple and red lines represent our GPR carts. We did one pass
over and back for each cart. The purple is our 170 and 600 megahertz GPR sled, and the red line is our 70 and 300 megahertz GPR cart.
So once we get all of this data, we have to actually process it to get it into a form that we can interpret. So for gravity, we initially did drift and instrument tie corrections. This profile right here shows the gravity profile after doing that, and you can see that the instruments line up, but the gravity profile is very much controlled by that terrain, the slope that the survey line was on, as Molly was talking about. So we had to do free air and Bouguer corrections for that, and that just entailed considering the distance between the gravimeter and the center of the Earth, and then the mass density between that distance or throughout that distance. And because our survey line was also going along the side of a cliff, essentially, we had to do advanced terrain corrections using LiDAR digital elevation model, which accounts for the elevation of the surrounding area all around our survey.
And so for GPR processing, we use a software called Geologic, and it's shown here on the right side. And basically, we can see before we added the manual gain, you can't really see any of the reflections at all. But then once we added the process of the manual gain, as well as these processes on the left, we were able to see some of those reflections. Also, you can see hyperbolas, clear hyperbolas there, right there. That will let us identify different subsurface features. And then also below that is the A-scan and the FFT before and after adding that manual gaining process. And the A-scan basically will show us the amplitudes in times of the EM wave traveling, and this is a single trace. And we can see that before it's a very small amplitude, as well as does not travel far in time. But afterwards, it gets a lot stronger as well as goes further in time. And then the FFT, or the fast Fourier transform, is getting our signal stronger around that 70 megahertz frequency, which we use in, as well as reducing the noise.
So as far as our gravity results go, they are inconclusive as to whether we located a stable structured mine shaft, a collapsed mine shaft, or even hit the right target. This is because the terrain largely influenced our gravity anomaly or our gravity profile, as you guys all saw in the processing slide. So yeah, in the method slide, you saw that negative residual gravity anomaly that we would want to be seeing, and that is not what we are seeing here. So this led us to believe that our single line, our single gravity line, did not provide enough data to uniquely say anything about the mine shaft.
And for our GPR results, we can not identify where mine shafts are, specifically the ceilings. And this is because of a very highly conductive layer and near the surface in our survey area, and it basically eats up or attenuates our signal. And you can see that here in the 300 megahertz frequency, there's nothing really there. It gets eaten up, and then afterwards there's noise provided. And same with the 70 megahertz frequency, just not as loud. And it shows right here a little bit, it goes away and then comes back as noise once again. And then we can say that this layer is most likely clay, given our background from earlier in the slides. And so we could say a 70 megahertz frequency GPR cannot see past this clay, making it the data not applicable for finding these mine shafts.
So when using GPR, we have to consider the target that we're actually trying to image and then decide what frequencies we're going to use. In the field, we were working under the assumption that the depth to the mine shaft ceiling was between 4 and 10 meters, knowing that using higher frequencies, we would get higher resolution, but our signal wouldn't travel as long or as deep into the subsurface. And then lower frequency data has lower resolution, but it travels farther into the subsurface. And the longer wavelengths of the lower frequency allows this signal to travel deeper into the earth through the more conductive clay layers, like we had mentioned previously.
And so we really wanted to ask ourselves, what can we do to see the mine shaft? And so we came up with this survey that has 3 methods, including ERT, or electrical resistivity tomography, gravity, and GPR. And the figure shows basically what our survey outlines will be, but in the next few slides, we're going to go more in depth about those.
So as far as our future gravity survey goes, we'll be using 2 CG5 instruments to construct a 60 meter by 30 meter grid with 4 meter spacing between each gravimeter station. So you can see in this figure of all of the mapped surveys The red dots signify the gravity stations, and we would take GPS measurements at every single one of these stations to account for elevation, and do all of those terrain corrections, as well as visiting base stations to account for time drift in the gravity measurements. And those would be visited at the beginning and end of every survey. And if your survey goes over multiple days, you would do it every single day. And ideally, this would take 5 to 6 hours to perform. And we justify our 4-meter spacing with this figure on the bottom right side. It is from a research paper where they essentially did the same thing. They made a grid with 5-meter spacing over top a known mine shaft, and they did see a negative residual gravity anomaly at that mine shaft location. So we know that this survey would be effective.
Cool. Atop the same 60 by 30 meter grid, gravity grid, we would want to run the 25 megahertz GPR cart across the grid with half-meter spacing between the grid lines. And the GPR grid lines are the black grid lines on that bottom left figure. And we would recommend using the 25 megahertz frequency because the longer wavelengths will travel farther through this conductive clay layer that we have identified at our site. And so hopefully leading for this future survey to possibly have our signals reach the ceiling of the mine shaft. We estimate the GPR survey to take anywhere between 1 to 2 hours. And this radargram here in the middle shows an example of void spaces previously identified by another research group. And this is just important to note because in the future, we would want to see reflectors like this, repeating reflectors on top of each other that would indicate a void space or a mine shaft in our case.
And finally, for our ERT setup, we'd want to use a 64 node setup with a 1 meter spacing, and this would give us a 63 meter line. And that's shown in the blue line in the middle. And we would extend this ERT along the gravity surveys we have. And then also we would want to use the dipole array first, and specifically for time constraints, because we're going to be lugging all this equipment up the hill, and that already might take time. And it did take away time from previous groups before. So dipole will provide the fastest as well as a very good lateral resolution, which we want. But for a backup array, if we have time, would be the winner. And we would do this with ABIM Walk Tim 2 instrumentation. And each of these arrays could take about 1 to 2 hours. And then on the right here is just a figure from a paper in Poland, basically showing where they found extending their mine plans and where they found voids, and through ERT basically showing that it is possible to find these cavities or voids through ERT.
And we would also like to say a big thank you to all of these individuals and organizations that made our entire field camp possible.
And I would also like to preface that the hunt is not over. We did not do all this future work for nothing. So ideally, we'll be doing this as a senior design project. And if not, we hope that future field camp groups can use these survey parameters to conduct their own surveys and find maybe the same mine shaft or different ones.
And here are some of our references.
A couple minutes for questions?
Yeah.
So you actually saw the mine shaft?
Yeah.
Our title page is a picture that
we did see it with our eyeballs.
This is it.
Did you penetrate into it?
Yes, and we palpated it.
Yes.
Palpated it?
Would that be safe, Bob?
I don't know if you've got somebody on a string.
It wasn't very deep. It was only like 4 feet into the side. It had caved in on that part.
Yeah.
It was closed off.
So initially we wanted to kind of characterize the mine shaft and see if maybe the section that we had been passing was collapsed or what the structural stability of it was. But as everyone saw, we couldn't do that.
Our data was not conducive to that.
Yeah.
Looking at the gravity data, you said that the, differences in the elevation was really your issue when it came to processing the data, for getting results. Do you think that having a 3D grid will fix that elevation issue?
Well, I think also where the 3D grid is, most of the area covers over that flat land, so it doesn't change elevation as much. So I think that would help a lot more. And in places it does, change in elevation, we would have to gauge once we get to the field if we want to do those areas or not.
Yeah, so over top our actual survey, from the gravity stations is 29 meters long. There was only about 3 meters in elevation change. So it was a very gradual slope over top this part of our survey. So if we extended a grid more west over the survey, it wouldn't have as extreme of a slope, and our farther western gravimeter stations wouldn't be as affected by this massive cliff right here. And the white, this is a generally flat area atop the hill. So
Yeah, I think we just want to get kind of a comprehensive understanding. So it was just basically like this 2D line was not effective. We'd need more like 3D understanding.
Move on, we can have time for questions at the end. Right, moving on to some laser scanning and a new technique for Geophysics Field Camp this year.
Yeah. All right, hi, my name is Krishna,
I'm Clara.
and our project is called Don't Block the Train. Just to give a quick overview, we're going to give some relevance and context of why we're doing this work, what data we collected in the field, what we did once we got the data and came back to campus, some interpretations based on our results, and end up with some conclusions. On all the slides after this, there'll be a box in the top right, and it will have a Roman numeral just corresponding to which section of the talk we're in. Also, shout out to the fearless Dr. Gabe Walton for taking this very illustrative photo of why we're doing this work.
Rockfall is a big hazard in Colorado, especially because we have a lot of railroads and car roads that go through the mountains with big rock outcrops over them. So this is just illustrating some of the rockfall hazards that have affected roads and train tracks. It can derail trains and cause rerouting. And so there is a lot of work by the Department of Transportation to mitigate these risks, and we're looking at more of this risk.
To give a little bit more fine scale context onto where we are doing, obviously we had our amazing field camp up in Steamboat. We are working at an outcrop that's right near Black Sulphur Spring. It's pretty accessible to the downtown Steamboat area. It's a pretty hot tourist destination because there's Black Sulphur Spring, and then right beyond it is Steamboat Spring. And as you can see in that bottom right photo, the rock outcrop that we were looking at is that outcrop right there, and it is right above an active Union Pacific Railway. Also worth noting is that outcrop is part of the Dakota group, and it's a sandstone, which will tie into some of our interpretations later.
The instrument that we used is called the terrestrial laser scanner, which sends beams out that will bounce off of the rock face and come back into the receiver of the instrument. So it's able to figure out the distance and orientation of all the faces around it. It has mirrors that rotate so that it can see up and down, and it's on a tripod so it can rotate side to side. So it has the capability to see in a 360-degree sphere around it. It has also a ranging unit that measures the phase shift in the returning wave, and that's how it figures out the distance away that the surface is to millimeters or centimeters. It can only see in its direct line of sight. So if there is something like this where the rock is coming out from the rest of the rock, it can't see behind that feature, and it can't see the sides. It can only see the side facing it. So that creates something called an occlusion. So we use this laser scanner at different locations along the cliff to see from different angles and try to see more sides of the rock.
For the actual field work that we did this past field camp, we went out to this rock outcrop near Black Sulphur Springs and collected a set of scans in the same location that Ellie collected them in 2025. Based on our parameters, we were able to have a resolution of between 6 and 10 millimeters. It's just based on the distance the actual target was from the scanner. There's less resolution the farther away it is. We took 4 scans, and the purpose of those 4 scans was to get around some of those line of sight limitations that Clara listed, because we wanted to image and scan the most of this cliff that we, most of this rock outcrop that we could. And there's these gully features that we want to get around. We had RGB data included this year, which is really helpful for the interpretability of our results. It made it a lot more feasible to look at it and understand what we were looking at in a 3D space. And it was about 6 minutes per laser profile. So the actual data that we end up with after all of this is a point cloud. And a point cloud is a 3D set of points where each point has its X, Y, Z coordinate, and it can also have some other information. And as we can see, as you zoom in, the density of the points and the spacing of the points really determines the size of the feature that we're able to resolve. So the denser the points we have, the finer scale features we're able to look at on a rock outcrop.
The first step that we did once we got the point clouds from the scanner is to register the scans together, which basically means to align them how they're supposed to be. When the instrument registers, or when the instrument collects them, it just sees them all right in front of it. So when we get the original scans, they're all just in a jumble together. So we have to arrange them to be how they really are. In the 2025 scan, we got it already registered from last year. So to minimize errors, we registered the 2026 scans directly onto the 2025 scan. So the first step in this was a manual course registration. So we looked at specific points that were the same on each of the scans and told the software to align those points. And then we were able to use an iterative closest points algorithm, which adjusted the alignment to minimize the error. From there, we were able to do a multi-scale model-to-model change comparison from the 2025 to the 2026 scans. So when we took the change from 2025 to 2026, we got a negative change where a rock had fallen, and that showed us this yellow arc, the backside of the rock that had fallen. And when we reversed that and took it from 2025 to 2026, then we got a positive anomaly, which showed us that front face in the brown line that was the front face of the rock that had fallen. So when we filtered out the background and just took out these two anomalies, we were able to get both the front and the back faces of the fallen rocks.
Cool. So once we have both the front and back faces of the rocks, we can go ahead and do some clustering. The idea behind clustering is that we take all our front and back faces of rocks and we use dbScan and MATLAB, and it assigns each what it thinks is a rock fall to a cluster. After that, what we'll do is we look at all of those clustered instances in Cloud Compare in 3 dimensions to make sure that they're all actually rock falls. What we're looking for is that there's a cohesive rock looking shape. And so some things that we filtered out where there were some small artifacts from vegetation around the edges of the point cloud. And then there was also some shallow soil erosion in kind of more scree areas of the outcrop that we're looking at. And we weren't interested in that. We were purely looking at rockfall instances. So we did some manual validation of all the clustered points that we got. That leaves us with something that we're able to put into a volume calculation. So we have this cleaned up cluster data set, and we can calculate the volumes of each of those clusters. We do that again in MATLAB by creating alpha shapes for each of those clusters and then calculating those volumes. That allows us to have a volume associated with each cluster, and we can visualize that very cleanly against our RGB data. This allows us to see the distribution and volume of rock falls across the rock face. So we can see there's areas where there's a lot more smaller rock falls, there's areas where there's some medium-sized rock falls, and then in the top left there, or top right, we have our largest rock fall. For a little bit of context, the largest rock fall was just under a half a cubic meter, which is slightly less than the size of a household dishwasher. And our smallest rock falls were around 70 cubic centimeters, which is the size of a jumbo egg, like the biggest egg you could probably get at the grocery store.
Another thing that we did with our point cloud data was to do a fracture set analysis. So we looked at groups of fracture planes, which are planes where the rock has broken, where it's weaker.
And each of the fracture sets is a group of those planes that have a same orientation. So we used the discontinuity set extractor in MATLAB, which for each point in the cloud assigns it a normal vector based on making a plane with its nearest neighbors. And then it groups each of the points that have similar normal vectors into a fracture set. The most dense fracture set that we see here is the blue one, which corresponds to the face of the rock slope, which is oversampled based on its orientation, and that's why that is the most frequent one. And then we have set it to have 4 sets, so we have the 3 other ones which are also shown.
So the big cumulative result of all this is our MCF plot. And the big takeaway from this is we're plotting the frequency per year in a spatially normalized way against the volume. And this tells us how often we expect to have certain size rockfalls. How often do you expect to have that little rockfall that's just a pebble the size of an egg, the big egg, or how often are you having a dishwasher come down? So we can do some statistical analysis here where we fit a line to this log space plot below what is known as the rollover point. And the rollover point is the point where this plot deviates from a nonlinear trend to a linear trend. Based on the slope and intercept of that trend that we're able to fit, we can compare the characteristics of the way that this rock outcrop sheds rock to other rock outcrops. So we were able to get 2 values in a spatially normalized space that were for our rock outcrop, and comparing that to an inventory of rock outcrops out there, there were very similar values for rock cuts in Morrison and Vale Pass. Both were also sedimentary rock cuts. So that kind of validates and makes sense with what we got.
In conclusion, terrestrial laser scanning is a really good method to document rockfalls. And if we had a little more time data, it could help us with predicting future rockfalls. This example just shows this is a photo taken by Ellie in 2025, and there's this big boulder here and a smaller rock here that we don't see in our photo from 2026 that Gabe took. There's very clearly shows in our analysis where those 2 rocks are and their volume bands.
Going into a little bit more of the future work, more future work can be done with the fracture set that we created or more fracture sets that are created using similar methodologies to do a kinematic analysis and learn more about the actual failure mechanism of rockfall. We kind of are thinking that it's more of a sliding failure in this case, but toppling failures are also possible, and maybe it varies across the rock outcrop. We can also compare this MCF result to other outcrops around the world, as well as adding our information to just publishing it out there so that others can compare to what we found here. And then just doing more scans of this face in future field camps or other field outings will help with a longer time series and a more robust understanding of what's going on.
Finally, we have some thank yous. We want to especially thank Gabe and Ellie for helping us with the data collection and processing of this. We want to thank the Union Pacific Railroad for allowing us to do this survey, and everybody involved in the Geophysics field camp, and Ryan for this sticker.
Time for a question or 2?
This is a question from me, not online.
Okay.
So you have a lot of these small rock falls, a bunch of these big rock falls, and you only have a year separation in the data. Do you think that these are all one event? Do you think some of these might be smaller events all kind of from the same place? Like, what's your take here?
It's interesting, and I think it's something that would be really helpful to go with a higher frequency of sampling of this rock face to figure it out. We were seeing that there is kind of some clustering of the smaller rocks in a certain area and the larger rocks in a slightly different area. So it'd be interesting to do a lot more frequent surveys on this smaller area and then the area where the bigger rocks are coming from to learn more about it. But in my background, I don't have a reason. Yeah.
I'd actually be curious, like how confident you are in all of the egg-sized ones, you know, because the cloud, resolving that you did and just where GPS points and stuff are, like, could have an egg worth of error in them, I wonder.
We filtered out all of the changes that were less than 3 centimeters. So the egg-shaped ones should all be more than our level of error. But there is also possibilities. We tried to go through and look at each of the clouds and make sure it looked like actual rock outline. There were a lot where there was kind of some occlusions behind rocks and that just had sparse points that made potential egg rocks, but we filtered those out because they did not look like rocks.
Did you guys talk to the railroad? Are they conducting similar kinds of studies at this location?
They were saying that this rock face is not one of their bigger concerns. They have other sections that have much higher hazard for them. So this specific site was not one that they've studied.
Yeah.
Could this have predictive possibilities over time in some of the areas that UPRR thinks are critical?
Yeah, if we had a better time series, then using the plot that Krishna talked about, the log plot, then that would give us kind of an expectation of how frequently each sizes of rock falls would be expected to happen.
Thank you. Right, we now are going to bring Raquel. She is up to need a little bit of Q&A and discussion for the end, and then we'll do 1 or 2 wrap-up minutes at the very, very end.
Hello, everyone. To start out our Q&A, we're just going to do a little recap in case you forgot about anything from the amazing presentations. So first, we had our seismic and geologic insights into the Yampa River Basin, processing, modeling, and interpretation, where we got to see some really cool fault interpretations going on and just a cross-section of the Yampa River. We also had characterizing Travertine deposits in Steamboat Springs, Colorado, at 2 main sites. I didn't get a picture for this group in time, but it was a great picture when they did send it. Sipping from the same source, a multi-physical analysis of the Lithia-Critter spring system, where we found that we're pretty sure that they are sipping from the same source. And we got the Sulphur Spring Cave, a study to evaluate GPR surveying for near surface seismic. I think that those findings were really cool. I think that was a great project. And another one without a picture, very sad. The geophysical hunt for the historic Onyx mine, which I think shows a lot of the value in survey design, future survey design. Another one without a picture, very sadly. Don't block the train, quantifying rockfall with terrestrial laser scanning, which you just saw. So I hope you didn't already forget about that one. Before we go into the questions, I just want to give one last huge thank you to everyone involved in field camp this year. Without all of these people, we couldn't have made these great projects happen. So big thank you to all of you. And now ask us anything.
Floor is open.
Yes.
There are a couple online questions still floating out there.
Okay.
First one was about the fault that got identified. Stuart Williams was curious if the river has influenced the creation of the fault versus the fault creating the river.
Is Stuart gonna be able to hear me from over here?
Yep.
Okay, so from one of our main interpretations, we saw that our fault went through upwards to our Browns Park formation. As a part of this, we think that possibly the river followed the fault instead of creating the fault, just based on also our alluvial deposits as well as our glacial deposits. The biggest thing with the glacial deposit, it's also alluvial, and likely as a result of that river and the deposition from the river. So one of our interpretations is the fact that the river came through and followed the fault and then left its deposits overlying the fault.
think Stuart
Great
will
answer.
accept that answer. I can keep going with online questions. This was a good one from Aspen. What differences would you expect to see in the historic mine shaft that is under the groundwater table versus above? Would that change what methods you use for distinguishing mine shafts that are saturated?
You would definitely want to prioritize gravity over GPR or because GPR would most likely be the signal would attenuate much faster in that mineral rich groundwater and likely wouldn't be able to reach the actual mine shaft ceiling and give us reflectors back. But gravity isn't affected by the like conductivity in the subsurface. It's just affected by the actual mass underneath your gravimeters and the mass around the gravimeters.
Yes, during your evaluations of all your subsurface investigations, there's in this valley of Steamboat Springs, there's probably numerous water wells that have been drilled. Have you considered accessing the Division of Water Resources database that's available and looking at the drilling log information and trying to integrate that into your interpretations?
I can answer that. So for the seismic survey, one of the biggest things that we were looking for was accurate wellbore data, but it became very, very difficult to find, with the most useful data being very, very far off from where our survey regions were. So one of the most, I guess, accurate wellbore data that we had that also told us the different geologic layers was north of Steamboat, which was away from our survey lines. So we didn't necessarily think that the information from that would be extremely applicable to where our surveys were. We did a lot of research and searching for different wellbores that could be used, but a lot of them did not have any coherent information that was extremely beneficial to us, at least on the larger scale.
Joe.
One of the kind of themes I saw throughout was a attempt to use gravity. So it kind of leads me to this question. If you guys could go back 4 weeks ago, how yourself, what would you have done differently?
Arthur's definitely a grid, and we had some issue with our GPS measurements in the middle of our survey. There was a disconnection from the base station, and then when it reconnected to the MLID, we believe there was like a like the number had reset to the like first. Yeah, the beginning of the line. It gave us a meter jump. Is that what you're talking about? Yeah, it did. But when it disconnected from the base station and reconnected, our GPS on the actual MLID tablet was telling us that the height to the actual DGBS was like 1.97 meters, when in reality we were at like 1.83 or something. So the GPS measurements that we had taken after it had reconnected, they were off, and then we had to correct for those in processing after realizing that. And we would definitely want to do a grid for ours at least.
I would say for the reflection seismic group, gravity has a pretty high time cost, and I would probably use that time to maybe shoot more reflection seismic or set up further seismic lines. I don't think it would be an incredibly effective method there, considering the time constraints.
And then I would say for our group, looking at Lithia-Critter Springs, I just wouldn't use gravity again. Especially depending on the porosity of the Travertine, the density difference that we would see between the soil and the Travertine would be very small. And so any positive anomaly that we would find would be very difficult to locate. And with the time constraints, or at least the time that it takes to execute a gravity survey, to make a grid over that whole area with fine enough spacing to resolve an anomaly of the Travertine, it just seems like it would be a lot better to do more extensive GPR, near surface seismic, and ERT in the area.
So did any of you find you had tools that allowed you to see subsurface water in any way? If somebody from the community wanted to find or map their hot springs, do you have a tool that you could use to help?
Yeah, electrical resistivity tomography is sensitive to like changes in conductivity, and once water saturated, it gives us a contrast. So that's a really beneficial method for that sort of stuff. Is that what you're asking?
Well, because one of the comments from the community was that they have all these little hot springs, like the Critter hot springs that show up, and they don't know where they are. You know, I mean, so they don't know if they're coming from some fault or fracture, or if they're just flowing through the landslide deposits. And that's true across the road as well, where the iron springs are located. So it just seems to me that it'd be interesting to guide some of the geophysical observations towards some of the community questions, which might be more pragmatic about where's the water going anyway. And if you could lay some groundwork for future people next year.
I will say we, my group tried to do a GPR and then the gravity survey, GPR survey by that black sulfur spring to kind of map that water pathways. And unfortunately, all we could really see were the tree roots. And then when we tried to do the gravity survey, that also didn't really show that water pathways. We tried to do that with those surveys.
I would probably say that DC resistivity is going to be the best for imaging water specifically, because you're going to get that really big resistivity change. And then I think that mapping travertine in areas can give indications of that water flow historically, or also potentially continuously if we're seeing it really close to the surface. But based on the tools that we've used and our knowledge on mapping groundwater, I think that those are the main things we'd be looking for in trying to accomplish that.
Overall, this is not a technical question. When you're experiencing your times there at summer camp, what do you think, in a general sense, what are your more interesting, exciting times versus your challenging times that you had?
I think that learning more about the geology, this is from my perspective, learning more about the geology of Steamboat, I had so much hope of all the cool projects you can do. And then you realize how limited you are on time and manpower and carrying equipment to the spot that you want to survey. So that was kind of challenging. And then you also get, wow, this is such a cool project. I'm so excited to have a week and a half to be able to produce something really cool. And then you go and you start looking at data and it's noisy and you don't know how to process it. And then you're processing it and it doesn't tell you what you were hoping it was going to tell you. So I think that getting disappointed by results was something that was really challenging, because like my group really wanted to definitively be like, that's such a clear travertine deposit. That's awesome. And we did not get that. And I think a lot of groups experienced similar things.
Speak up, anybody.
I'll add on, one of the best parts of field session for me is the fact that we get a lot of choice in what we do. At the beginning of the day, we know what method we're going to use, but we don't know where exactly we're going to go, aside from the already laid out seismic line. But having that freedom of choice and understanding what we can do with the different tools, for me at least, was extremely in a sense satisfying. It gave me a sense of fulfillment, and I already know what I'm going to use, but how can I use this in different areas was, again, really nice to be able to do.
I think also extremely satisfying is still reflection seismic, just being able to see and actively working on that data, seeing how that work that we've done outside for that whole week and a half period, and just seeing how that translates into data that we can manipulate and we can look at and we can interpret something from it is just extremely satisfying. It's just how that entire process unfolds in front of you in such a short time span.
I will say ground penetrating radar is extremely interesting to me, because as you're doing the survey, you get a live view of the subsurface on your radar gun on an iPad, and I think that's really interesting because you can be like, oh, that's a reflector right there, but I don't think that there's anything in the subsurface there. And then you think about it and you're like, oh, there's an alpine slide 4 feet to my left. This looks like the same two-way travel time. Let's work this backwards and be like, okay, that's probably not something in the subsurface. You can walk around and see exactly what's underneath you and kind of around you in live time. And there's not really any other methods that show you that. And it's cool.
I think for me, it was really interesting seeing, like, we've learned kind of all of these methods before and applied one and applied two, but most of them we were applying just on like capital commons, actually being able to take that and apply that to like real world scenarios, being able to kind of find things really interesting.
Any laughs along the way?
I didn't hear a single one the entire time. I've been here for 4 weeks, no laughs.
We actually said we were not allowed to have fun.
Yeah.
True. Must be coming to your business.
All right, I think we've had a wonderful 2 hours of discussion and presentations. Just to remind everybody, I just want to congratulate the students on the impressive amount of work they've done. Just to put this in context, they left Golden on May 17th. They returned to Golden on May 29th. They started looking at their data in earnest on June 2nd, and it is June 11th, and this is what they produced from it. So I'd just like to thank the students for everything that they've done in the last month. Amazing work, and I look forward to reading the reports tomorrow. Those who are around, all the students and anyone in the audience, we are having a barbecue tomorrow starting at noon on campus in the Marcus atrium. In case it's too hot or rainy or golf ball sized hail decides to embark upon us, you're all welcome to join and chat some more, ask more questions about the laughs or the lack of laughs that happen at field camp. And we'll be back again next year on roughly the same date if you want to come back and see it again. Thank you, everybody.